Hi friends, in this session we have evaluation of improper integral. In calculus, the improper integral of a continuous function f(x) over the semi-infinite interval 0 less than or equal to x less than infinity is defined by means of the equation integral over 0 to infinity f(x) dx is equal to limit r tending to infinity integral 0 to r f(x) dx. Equation number 1. When the limit on the right of equation number 1 exists, the improper integral is said to be convergent to that limit. If f(x) is continuous for all x, its improper integral over the infinite interval minus infinity less than x less than infinity is defined by writing integral minus infinity to infinity f(x) dx is equal to limit r1 tending to infinity integral over minus r1 to 0 f(x) dx plus limit r2 tending to infinity integral over 0 to r2 f(x) dx. Equation number 2. And when both of the limits here exist, we say that integral 2 converges to their sum. Next, Cauchy principal value. Another value that is assigned to integral 2 is often useful. It is the Cauchy principal value that we write as CPV of integral 2. The Cauchy principal value of integral minus infinity to infinity f(x) dx is defined to be, that is Cauchy principal value, that is CPV, minus infinity to infinity f(x) dx. This is equal to limit r tending to infinity minus r to r f(x) dx, provided the single limit exists, which is equal to limit r tending to infinity integral over minus r to r f(x) dx. Equation number 3. Next equation number. This single limit exists. Theorem. If integral minus infinity to infinity f(x) dx converges to a, then CPV of minus infinity to infinity f(x) dx exists and CPV integral minus infinity to infinity f(x) dx is equal to a. Proof. If integral minus infinity to infinity f(x) dx converges to a, then a is equal to limit minus integral minus infinity to infinity f(x) dx, that we can write as limit r1 tending to infinity integral minus r1 to 0 f(x) dx plus limit r2 tending to infinity 0 to r2 f(x) dx. That is, we can write a is equal to limit r1 tending to infinity integral minus r1 to 0 f(x) dx plus limit r2 tending to 0 infinity integral 0 to r2 f(x) dx. Equation number 4. Also, limit r tending to infinity minus r to r f(x) dx is equal to limit r tending to infinity, we can write it as integral minus r1 to 0 f(x) dx plus integral 0 to r f(x) dx. the last two limits in the above expression are the same as the limits on the right in equation number 4. Hence, left side of 4 and the fifth equation, that is just above we have said, are the same. That is, we can say A is equal to integral minus infinity to infinity fx dx. This is equal to limit r tending to infinity minus integral over minus r to r fx dx. Hence, Cauchy principal value, that is my integral minus infinity to infinity fx dx is equal to A. Example. Cauchy principal value, integral CPV, integral minus infinity to infinity x dx. Here our fx is x, which is equal to limit r tending to infinity integral minus r to r fx dx. Instead of fx, here fx is x. So, it is x dx, which is equal to limit r tending to infinity integral minus r to r x dx. So, it becomes x square by 2 over the limits minus r to r, which is equal to limit r tending to infinity r square by 2 minus r square by 2, that is, which is equal to limit 0. R tending to infinity, limit 0 is equal to 0. On the other hand, integral minus infinity to infinity x dx is equal to limit r1 tending to infinity integral minus r1 to 0 x dx plus limit r2 tending to infinity 0 to r2 x dx. It is again limit r1 tending to infinity x2 by 2 over the limits minus r1 to 0 plus limit r2 tending to infinity x square by 2 over the limit 0 to r2. So, that becomes it becomes which is equal to minus limit r1 tending to infinity, what in first integral it becomes r1 square by 2 plus again we have limit r2 tending to infinity, the value is r2 square by 2. And since these last two limits do not exist, we have integral minus infinity to infinity x dx fails to exist. Next theorem. Suppose that fx, that is minus infinity less than x less than infinity, is an even function, so that f of minus x is equal to f of x for all x. That is f of minus x is equal to f of x. And assume that the Cauchy principal value 3 exists. Then integral minus infinity to infinity fx dx and integral 0 to infinity fx dx exist. This exists and integral minus infinity to infinity fx dx is equal to, that is this one. We can say integral minus infinity to infinity fx dx is equal to Cauchy principal value, that we can write as CPV of my integral minus infinity to infinity fx dx. Equation number 6. Again integral 0 to infinity fx dx is equal to 1 by 2 times CPV, that is Cauchy principal value of integral minus infinity to infinity fx dx. Equation number 7. Proof. The symmetricity of the graph of y is equal to fx with respect to the y-axis tells us that integral minus r1 to 0 fx dx is equal to 1 by 2 times integral minus r1 to r1 fx dx, and integral 0 to r2 fx dx is equal to 1 by 2 times integral minus r2 to r2 fx dx. Thus, integral minus r1 to 0 integral minus r1 to 0 fx dx plus integral 0 to minus r2 fx 0 to r2 not minus 0 to r2 fx dx is equal to 1 by 2 times what? Integral minus r1 to r1 fx dx plus 1 by 2 times, next one is 1 by 2 times integral minus r2 to r2 fx dx. That is integral minus r1 to 0 fx dx plus integral 0 to r2 fx dx is equal to integral minus r2 to r2 fx dx. If we let r1 and r2 tend to infinity on each side here, the fact that the limits on the right exist means that the limits on the left do too. Hence, limit r1 tending to infinity integral minus r1 to 0 fx dx plus limit r2 tending to infinity integral 0 to r2 fx dx is equal to limit r tending to infinity integral minus r to r fx dx. That is integral minus infinity to infinity fx dx is equal to Cauchy principal value, that is CPV, integral minus infinity to infinity fx dx. Moreover, since integral 0 to r fx dx is equal to 1 by 2 times integral minus r to r fx dx. Limit on the right exists means that the limit on the left do too. Hence, limit r tending to infinity integral 0 to r fx dx is equal to 1 by 2 times limit r tending to infinity integral minus r to r fx dx. That is integral 0 to infinity fx dx is equal to 1 by 2 times what? CPV, Cauchy principal value, integral minus infinity to infinity fx dx. Next, we have method involving sums of residues. We now describe a method involving sums of residues that is often used to evaluate improper integrals of rational functions of the form fz is equal to pz by qz. That is fz is equal to rational form pz by qz. Equation number 8. Where pz and qz are polynomials with real coefficients and no factors in common. We agree that qz has no real zeros, that is no zero on the real axis, but has at least one zero above the real axis. Then fz has no real poles, that is no pole on the real axis, but has at least one pole above the real axis. The method begins with the identification of all the distinct zeros of the polynomial qz, that is the poles of fz that lie above the real axis. They are of course finite in number because a polynomial of degree m has at most m distinct zeros and may be labeled like z1, z2, etc. zm, zn, where n is a number less than or equal to the degree of q set. We then integrate the quotient, that is f set is equal to p set by q set, around the positively oriented boundary C of the semicircular region shown in the figure. The simple closed contour C consists of the segment of the real axis from z is equal to minus r to z is equal to r, and the top half of the circle mod z is equal to r described counterclockwise and denoted by CR. We choose the positive number r large enough so that the points this one Z1, Z2 etc. Zn all lie inside the closed path. Then by the Cauchy's residue theorem, we have integral over C f z dz, which is equal to 2 pi I sigma k varies from 1 to n residue at z is equal to zk f z. Equation number 9. Since the line segment of the real axis just mentioned have the parametric representation as z is equal to x, where x lies in between minus r and r, that is minus r less than or equal to x less than or equal to r. And since C is a union of this line segment and CR, it follows from equation number 9 that integral minus r to r fx dx plus integral over CR f z dz is equal to 2 pi I times, that is 2 pi I into sigma k varies from this one, sigma k varies from 1 to n residue at z is equal to zk f z. Z is equal to zk f z, or we can say integral minus r to r fx dx is equal to 2 pi I, that is minus r to r fx dx is equal to 2 pi I sigma k varies from 1 to n residue z is equal to zk f of z minus integral over CR f z dz. That is, we are taking this integral to the RHS, that is integral minus r to r fx dx is equal to 2 pi I sigma k varies from 1 to n residue of f z at z is equal to zk minus integral over CR f z dz. Equation number 10. If limit r tending to infinity integral over CR f z dz is equal to 0, it then follows from equation number 10 and the definition of Cauchy principal value that CPV integral minus infinity to infinity fx dx is equal to what? 2 pi I sigma k varies from 1 to n residue of f z at z is equal to zk. Again, if fx is even, equation 6 and 7 together with 11 tells us that integral minus infinity to infinity fx dx is equal to 2 pi I sigma k is equal to 1 to n residue of f z at z is equal to zk. Equation number 12. And integral 0 to infinity fx dx is equal to pi I times sigma k varies from 1 to n residue of f z at z is equal to zk. Equation number 13. Where the sum extend over all poles in the upper half plane, assuming that there is no pole in the real axis. Next example. Evaluate the integral 0 to infinity, our function is x square by x raised to 6 plus 1 dx. We observe that the function, that is f z is equal to z square by z raised to 6 plus 1 has isolated singularities at the zeros of z raised to 6 plus 1, which are the 6th root of minus 1, and is analytic everywhere else. Now the sixth root of minus 1 are obtained as follows. That is, minus 1 is equal to cos pi plus I sin pi, which is equal to e raised to I pi. Hence, minus 1 whole raised to 1 by 6 is equal to cos pi plus 2k pi by 6 plus I sin pi plus 2k pi by 6, which is equal to e raised to I into pi plus 2k pi by 6, where k varies from 0, 1, 2, etc. up to 5. That is, the possible roots of z raised to 6 plus 1 are given by Ck is equal to it is given by exponential I into pi by 6 plus 2k pi by 6. Where k varies from 0, 1, 2, 3, 4, 5. And it is clear that none of them lies on the real axis. The first three roots, that is C0 is equal to e raised to I pi by 6, C1 is equal to I and C2 is equal to e raised to I 5 pi by 6, lie in the upper half plane, and the other three that lie in the lower one. When r greater than 1, the points Ck lie in the interior of the semicircular region bounded by the segment z is equal to x, that is minus r less than or equal to x less than or equal to r of the real axis, and the upper half CR of the circle mod z is equal to r from z is equal to r to z is equal to minus r. Integrating fz counterclockwise around the boundary of the semicircle region, we see that integral minus r to r fx dx plus integral over CR fz dz is equal to 2 pi I times B0 plus B1 plus B2. Where Bk is the residue of Fz at a Ck, where k varies from 0, 1, 2. Taking Pz is equal to z square and Qz is equal to z raised to 6 plus 1. That is, here Pz is equal to z square and Qz is equal to z raised to 6 plus 1. Noting that P of Ck is equal to Ck square not equal to 0 and Q of Ck is equal to Ck raised to 6 plus 1. That is, Q of Ck is equal to Ck raised to 6 plus 1. That is minus 1 plus 1, which is equal to 0. And Q dash of z, what is the derivative of z raised to 6 plus 1? It is nothing but 6 z raised to 5. And again Q dash of Ck, it is 6 Ck raised to 5 not equal to 0. It follows that the points Ck are simple poles of f is equal to Pz by Qz, and Bk is equal to residue at z is equal to Ck, z square by z raised to 6 plus 1. That is Bk, that is residue at z is equal to Zk, z is equal to Ck, z square by z raised to 6 plus 1. That is residue at z is equal to Ck, what, Pz by Qz, or this can be written as it is P of Ck by Q dash of Ck, which is equal to Ck square by 6 Ck raised to 5, which is equal to 1 by 6 Ck cube, where k varies from 0, 1, 2. Thus, 2 pi I into B naught plus B1 plus B2 can be written as 2 pi I into B naught plus B1 plus B2. This is equal to 2 pi I into, substituting the values of B naught, B1 and B2, we get 1 by 6 I minus 1 by 6 I plus 1 by 6 I, which is equal to, on simplification we get it is equal to pi by 3. And equation 13 can be put in the form integral minus r to r fx dx is equal to this is equal to pi by 3, that is our 2 pi I into B naught plus B1 plus B2, its value is pi by 3 minus integral over CR f set dz, equation number 15, which is valid for all values of r greater than 1. If we assume that limit r tending to infinity integral over CR f set dz is equal to 0, then follows from 15 for using 11 that limit r tending to infinity minus r to r x square by x raised to 6 plus 1 dx is equal to what? Pi by 3 only. That is CPV Cauchy principal value CPV of minus infinity to infinity fx dx. Fx dx is equal to 2 pi I times sigma k varies from 1 to n residue at z is equal to zk f set. That is CPV minus infinity to infinity what fx is x square by x raised to 6 plus 1 dx, which is equal to pi by 3. Since the integrand here is even, we know from equation 7 in theorem that integral 0 to infinity x square by x raised to 6 plus 1 dx is equal to pi by 6. Verification that limit r tending to infinity integral over CR f set dz is equal to 0. We now show that the value of the integral on the right in equation number 15 tends to 0 as r tends to infinity. To do this, we observe that when mod z is equal to r, that is when mod z is equal to r, that is mod z square is equal to, we can say mod z square equal to mod z square, which is equal to r square. And by an application of triangular inequality, we can write modulus of z raised to 6 plus 1 is greater than or equal to modulus of z whole raised to 6 minus 1. Again here we have again modulus, which is equal to mod z raised to 6 is what? It is r raised to 6. So, I can write it as r raised to 6 minus 1, or 1 by z raised to 6 plus 1, 1 by modulus of z raised to 6 plus 1 can be written as, it is less than or equal to 1 by what? R raised to 6 minus 1. When mod z, that is mod z is equal to r, it is mod z is equal to r. So, if z is any point on CR, mod f z is equal to mod z square by mod z raised to 6 plus 1, it is less than or equal to mr where that mr is equal to r square by r raised to 6 minus 1. And this means that modulus of integral over CR f z dz is less than or equal to, that is modulus of integral over CR f z dz, it is less than or equal to this mr into integral over CR dz, which is equal to what? Which is equal to mr into integral over CR dz is what? Pi r. Equation number 16. Next equation number is 16. Pi r being the length of the semicircle CR, this is obtained using ML inequality that we have discussed earlier. Since the number mr pi r, which is equal to mr pi r is equal to pi r cube by r raised to 6 minus 1 is a quotient of polynomials in R, and since the degree of the numerator is less than the degree of the denominator, that quotient must tend to 0 as R tends to infinity. More precisely, if we divide both numerator and denominator by r raised to 6 and write mr pi r is equal to, that is dividing throughout by r raised to 6, we can write it as mr pi r is equal to pi by r cube divided by 1 minus 1 by r raised to 6. It is evident that mr pi r tends to 0 as r tends to infinity. Consequently, in view of inequality 16, limit r tending to infinity integral over CR f z dz is equal to 0. L'Hopital's rule. Let f z and g z be analytic in a region containing A if the fraction f z by g z assumes one of the indeterminate forms, that is 0 by 0 or infinity by infinity when z is equal to A, and if limit z tending to A f dash z by g dash z exist, then limit z tending to A f z by g z is equal to limit z tending to A f dash z by g dash z. A similar statement holds if the indeterminate form arises when z becomes plus or minus infinity instead of when z is equal to A. Next example. Evaluate integral 0 to plus infinity dx by x raised to 4 plus a raised to 4 if a greater than 0. Here a greater than 0. Since 1 by x raised to 4 plus a raised to 4 is an even function, we have by theorem integral 0 to infinity 0 to plus infinity dx by x raised to 4 plus a raised to 4 is equal to what? 1 by 2 times CPV, Cauchy principal value, integral minus infinity to infinity dx by what? Dx by x raised to 4 plus a raised to 4. Consider the function, that is f z is equal to 1 by z raised to 4 plus a raised to 4. The poles of this f z are given by the equation z raised to 4 plus a raised to 4 is equal to 0. That is z raised to 4 is equal to a raised to 4 into cos 2n plus 1 pi plus I sin 2n plus 1 pi. That is z is equal to, we can say z is equal to a into cos 2n plus 1 by 4 pi plus I sin 2n plus 1 by 4 pi. When n is equal to 0, 1, 2, 3. Hence, poles are at a into cos pi by 4 plus I sin pi by 4 is equal to a into e raised to I pi by 4. That is a cos 3 pi by 4 plus, I am taking a as a common factor, a into cos 3 pi by 4 plus I sin 3 pi by 4 is equal to a into e raised to 3 pi by 4. That is a into cos 5 by 4, 5 pi by 4 plus I sin 5 pi by 4 and a into cos 7 pi by 4 plus I sin 7 pi by 4. The last two poles are not in the upper half plane. Hence, integral minus infinity to plus infinity fx dx is equal to, which is equal to 2 pi I into r1 plus r2 plus, where r1 plus is equal to residue at z is equal to a into cos pi by 4 plus I sin pi by 4 1 by z raised to 4 plus a raised to 4, which is equal to limit z tending to a into e raised to I pi by 4 z minus a into e raised to I pi by 4 into 1 by z raised to 4 plus a raised to 4. Its value is, that is, this r1 is equal to r1 is equal to 1 by 4a cube into cos 3 pi by 4 plus I sin 3 pi by 4. And similarly, this r2, this r1 plus. Similarly, r2 plus is equal to residue at z is equal to a into cos 3 pi by 4 plus I sin 3 pi by 4 1 by z raised to 4 plus a raised to 4, which is equal to 1 by 4 a cube into e raised to I 9 pi by 4. That is equal to 1 by 4 a cube into cos 9 pi by 4 minus I sin 9 pi by 4. That is r2 plus, it is equal to 1 by 4 a cube into, it is cos 9 pi by 4 minus I sin 9 pi by 4. Hence, integral minus infinity to infinity dx by x raised to 4 plus a raised to 4 is equal to integral minus infinity to plus infinity fx dx, which is equal to 2 pi I by 4 a cube into cos 3 pi by 4 minus I sin 3 pi by 4 plus cos 9 pi by 4 minus I sin 9 pi by 4. That is, its value is integral minus infinity to plus infinity dx by x raised to 4 plus a raised to 4, which is equal to 2 pi I by 4 a cube into, in the bracket, its value is minus 1 by root 2 minus I into 1 by root 2 plus 1 by root 2 minus I into 1 by root 2. Values of cos and sin, which is equal to, on simplification, which is equal to pi by root 2 into a cube. That is integral 0 to plus infinity dx by x raised to 4 plus a raised to 4 is equal to 0 to plus infinity dx by x raised to 4 plus a raised to 4, the value is equal to pi by, that is 1 by 2 times pi by 2 root 2 a cube. Here in this session we discussed Cauchy principal value and method for finding sum of residues. Thank you for watching this session. See you next time. Till then, take care.